In most of the metallurgical processes, all the metallic minerals of industrial interest are subject to extractive and separation operations, where oxidation and reduction agents are also involved. For example, see this chemical equation. As you can see, the process of hydrogen gas must be relevant for the limit of reaction step in the redox mechanisms due to the capacity to convert all the iron oxide into the direct reduced iron, which is the material also called DRI. This little equation suggests that both reagents and products find each other in different phases. That means that the limit step for this reaction can also be limited by the mass transfer properties involved in the iron/iron oxide interface on this reaction. Consider a conventional metallurgical process where this chemical reaction occurs at 400 Kelvin and 1 atmosphere. If we assume that the iron oxide layer substrate is non-porous and the iron layer cytosides is porous, the mass transfer of hydrogen can be modeled according to the next diagram. We need to consider that as iron oxide is reduced to iron, the interface location established by delta will move down with respect to a zero position. For modeling the transport of hydrogen, we need to consider the following assumptions. 1. The process is carried out in a pseudo-steady state. 2. The hydrogen only diffuses through z-axis. 3. There is no chemical reaction through the controlled volume. And 4. The temperature and pressure remains constant. On the other hand, for calculating the time required for iron oxide consumption with the macroscopic mass balance, we must consider the following assumptions. 5. There are normal flow that indicate the entry or exit of iron oxide. 6. There is normal flow of generation of this component. And 7. The reaction is very rapid so that the reduction of iron oxide is limited by the hydrogen diffusion. Taking into account these statements, we can count the microscopic mass balance for hydrogen through the porous layer. So, if we apply the assumptions 1, 2, and 3, the mass balance can be reduced as below. Calling the general Fick's law for hydrogen flux, we can also apply the assumption 2 to reduce it as below. Since we know that the molar flow of hydrogen can be calculated following the stoichiometry numbers from the chemical equation presented before, we can substitute the result flux relation into the Fick's law. So, if we substitute the Fick's relation into the mass balance and apply the assumption 4, this action will give us a second-order differential equation, where the molar fraction is the dependent variable and the zeta position through the porous material becomes the independent variable. If we establish that at zeta equal to 0, the molar fraction of hydrogen is 1, and also at zeta equal to delta, the molar fraction of hydrogen is equal to 0, we can solve the equation by normal integration. Thus, we obtain an analytical function where the molar fraction of hydrogen is described in terms of the zeta position. If we place this result into the Fick's law equation and we call the assumption 5, the molar flux of hydrogen within the porous iron layer can be deduced according to the interface position, which is an iterative result. Or also, if we write the total concentration in terms of gas properties using the ideal gas law, for example, the molar flux and molar distortion of hydrogen through the surface reaction can be calculated according to these expressions. Finally, if we replace delta equal to 1 cm into the flux equation with the known parameters and we are careful with the dimensional analysis, we can deduce finally that the flux at the beginning of the iron oxide consumption must be equal to 0.5183 moles per meter squared per second. By the other hand, if we call the general macroscopic mass balance for iron oxide through the non-porous bulk material and we take into account the assumptions 5, 6, and 7, these equations can be reduced to the first-order differential equation that describes them, where the time is the independent variable and the delta, the interface location, is a dependent variable. Integrating from 0 to tau are parameters that I define for time, and delta is equal to 2 cm and the initial delta for the integration is 1 cm, we can obtain finally an analytical model that allows us to calculate the required time to consume all the iron oxide layer, knowing the interface position of this material. So, if we substitute carefully, the required time needs for this process needs to be 16.78 minutes. But analytical results are also awesome to clear out how the grinding concentration of hydrogen can change with time as iron oxide gets consumed, since the domain of the function solution of the mass transfer differential equations will instantaneously change as the value of delta increases. Check out! This does not imply that the process is transitory. but rather that the process changes its mass transfer properties instantaneously to remain in a steady state as the position of the boundary increases. This situation does not actually occur because the more dimensions of the control volume, the more difficult it will be for the system to change fast enough to maintain the mass balance without changing the adherent concentration in the porous air layer. In conclusion, the analysis of the flux and concentration profile for this process made possible to study the influence of initial and boundary conditions on the speed and time required to reduce the iron oxide. However, it's essential that for future work, other thermophysical properties and multiple reactions should be considered for future sensitivity analysis in which the optimal time can be estimated with less economic, environmental, and safety repercussions.